All right, so this is exploit development. Here, everything you need to do this class is on samsclass.info. There is a Canvas course management system that the college wants you to use, and that's where you go to take quizzes and where to turn in your projects and such. So you can start there, but the detailed instructions for the projects are here on this page, samsclass.info, CNIT 127. And all right, so the class is live streaming on Twitch where you are right now. If you don't want to watch it live, or you can't, you can just watch the videos. I record YouTube videos and I put them on this page. This schedule will have videos, so you can watch the lecture asynchronously. All right, and there's a lot of homework projects to do, and lectures and quizzes. So let me get the first day handout, which is here. Okay, here's the grading policy. Yes. All right. So there's quizzes, there's projects, and there's a final exam. And that adds up to a bunch of points. 90%'s an A, 80%'s a B, 60%'s a C, and so on. This total may not be quite up to date. I haven't checked to make sure this is entire, but whatever the total is, it'll be 90%. There's a lot of extra credit. So what a lot of students do is they do extra credit projects to make up for any quizzes they do badly on, and to make up for the final. A lot of students don't even bother to take the final because they do extra credit projects instead. The projects are here, and you'll see there's a bunch that just have a number. Then those are ones I expect you to do, and they're worth that many points. And then there are ones that have all or part extra credit part, and you don't need to do those, but if you do, there are points to replace other things. And as you can see, there's a lot of credit, extra credit, 150.5 points extra for SQL injection, 35 for server-side template injection, and so on. There's a lot of extra credit, enough that you can just do hands-on projects and ignore everything else if you like, and that's fine. So this also gives you a quick summary of what we're going to cover. The point of this class is to learn how to take attacks and develop them into better exploits. So we'll start with simple attacks that do command injection, where you can put data in something like a web form, and some of that data is misunderstood by the server as a command. That's the simplest kind of attack. And then we'll move into binary exploits, which require you to perform memory corruption and use a disassembler and examine the assembly code that you're injecting into a server's memory in Linux and then in Windows. And then there's a few extra credit things like ARM and such. Someone asked if this class is harder than practical malware analysis. I think it is, but not a lot. The practical malware analysis was just the other side, the defensive side of the same stuff. This is how you write the malware. But I think this one is a little bit more technical. Good. I see some good answers there. Yeah, I threw in some Rust, because Rust is the new cure for all this. All these memory corruption exploits that we do up here, like buffer overflows and format strings and heap overflows, are all fixed by using Rust pretty much. And so I put in some Rust so you can see why people love Rust. The point of Rust is it is a memory-safe language. Most of the problems that cause these vulnerabilities do not happen if you write your code in Rust. All right. So, let's see, there was another, the syllabus I don't think we need is the same as this page. So let me find my lecture. Chapter 1 should be here. Yep. All right, good. All right, so I'm going to start talking about this stuff, and if people have come to add or anything, we'll do that at the break to make sure everybody has time to make it in. And if you miss a class or you come late to a class, that's fine. Like I mentioned, everything will be archived on my webpage, so you can view it later if you want to. You can also completely ignore my lectures if you like and read the book or just do the projects. You know, you're not graded on the lecture or on attendance, just on doing projects or quizzes. All right, so here's what your book regards as basic concepts. This book is pretty advanced and pretty hard to read, you might notice. So we're only going to cover a portion of this book, and I try to make the part I cover easier. But this book assumes that you already know assembly code before you start, so that's the first thing we have to cover, because I certainly don't expect you to already know assembly code. Most students don't, and this class did not have the assembly code class as a prerequisite, so we're going to cover the essentials of it. You do not have to be a very good assembly code programmer to do what we're doing here, but you do need to learn a few of the basics. So, here's the basic concepts. So a vulnerability is a flaw in your system that lets the attacker do something they shouldn't be able to do. Like there's some way to shut down the server or render it unavailable. There's some way to elevate privileges to become the administrator without a real administrator login. Some way to execute code, which the developer did not intend for you to do. The developer typically only wants you to do certain things, and if you get to do something outside that list, that's a vulnerability. So an exploit is something that takes advantage of this and does something unusual. And people often call this a proof of concept. You find a vulnerability, and then you want to prove it's real, so you perform an exploit. Proof of concept. A 0-day is an exploit that has not been publicly disclosed, so nobody knows it exists, and therefore there will be no patch available for it. There will be no antivirus signature to detect the attempts, and that's the thing. The most valuable exploit is a 0-day from the viewpoint of an attacker, because there is no general way for anybody to detect it or prevent it. And then a fuzzer is sending a lot of random data to a server just to try to get it to crash, and that's typically how you start. You fuzz a server until you manage to crash it, and then you've got an idea. Let me see if I can fix this camera, which is just stubbornly doing stupid things to me. All right, you fuzz the server until it crashes, and that gives you a denial of service attack, and then you try to improve that to a remote code execution attack. All right. So what we're going to do here is memory corruption attacks. All the data in your computer is in the form of bytes, just ones and zeros, and your computer doesn't understand what any of it means. It doesn't know text from images, from movies, from code, and almost all the attacks we're going to use involve tricking it into entering data that it thinks is something like a username or a password, and then reinterpreting that as commands later. So it fundamentally relies on the fact that the computers don't really understand the significance of the data they're throwing around. All right, so that's what we've got here. All right. So when you run a program, you double-click Microsoft Word or something on a Microsoft machine, it loads the program into memory, and then you assign some memory regions to that program for its use. So it's got various segments of data that go up into RAM. There's types of data stored in a program and used in RAM. Text is the section that contains program instructions. Data contains initialized global variables, and BSS is the basic stack segment that contains uninitialized global variables. And there are other ones. So there are various regions of memory reserved for the use of that program. Now the stack is a last in, first out memory section, like a stack of trays in a cafeteria. You put them in, push it down, put another one in, and push it down. And when you pull one off, the one you take off is the last one you put in. So they come out in reverse order. Now the entire purpose of the stack is to do this thing called function calls, where I'm doing one thing, then I call a function, then that function calls another function, so I'm descending layers down logically like a dream within a dream. So I double-click Microsoft Word and it launches. Then I double-click File Open and it opens a file dialog box. Then I click the name of a file and it does something. I'm going into a function of a function. When it's done opening the file, it will return from that function and go back up to Word. When I close Word, it will leave Word and go back up to the operating system. That is what the stack is for. The stack lets you have data remembering where you are. I was at step 5 of the main function. Then I went through the print function. Then I was step 10 of the print function. I called another function and another function. And when I'm done with this one, I come back and pick up where I left off. So the stack is where the temporary information is stored for this process of a subroutine calling another subroutine, calling another subroutine. and typical computer programs are 20 or 30 layers deep in this at all times. That's why it's designed this way. It works very well, but it leads to a famous attack, the stack buffer overflow, which is what we're going to do for most of this semester, perform stack buffer overflows, which are the simplest memory corruption exploits and the ones that all others are based on. Now, the heap is a similar place to store temporary data, but it doesn't have this last in, first out priority structure. It's just unordered data. You just have lumps of data, chunks of data, and you can read and write them and erase them as you wish, just like objects stored on a shelf. So you can also have heap corruption attacks, but the heap is not involved in remembering temporary data as you traverse routines and subroutines. So it's really a simpler object than the stack in many ways. So here's an example of a program memory. You'll have the kernel of the operating system having some usually low memory, but it could be some anywhere. This is the essential part of the operating system that must always be in RAM. Then you've got the stack, which grows down as you keep, and you got the heap, which grows up, and then other sections down here like the text section that include instructions. So there will be various memory segments allocated to your program, and they will be used as your program runs. And all of the attacks we're going to talk about in the second and third part of the course will be talking about tricking it into misunderstanding data that's been put on the stack and other memory regions. All right, so let's try a Kahoot. If you haven't taken my classes before, you may not have used Kahoots, but these things are a little game show. This is worth extra credit. You don't have to do it, but it usually prevents students falling asleep so much. So let me bring up the first Kahoot, and it's worth extra credit if you are in the top 3 in any Kahoot. You get 3 points every time you are one of the top 3 performers in a Kahoot, and that can add up. So it's favorites. Okay. And there we are, 1A. Continue. Let's see if they've hidden my controls somewhere. Okay. Let me make sure I've got this set to. Come on, is it moving? All right. And there ought to be a show answers on players' devices. That's the most important thing, so you can see the questions. All right, this looks pretty good. Let's see how it works. All right, why is there no music? Well, anyway, you have to go to kahoot.it and put in that number, and then you can join. I don't know what happened to the music. There we go. All right. We do need the tunes, I agree. Okay, this is Jan 18. Good. All right, I'll give it a few more seconds, see if any more people are coming. Well, people are leaving. All right, there we are, back up to 17. Okay, All right. Let's give it a try. All right. All right. An attack with no known defense. All right, that's a 0 day, good. And it scores you both on accuracy and speed, so you can get up to 1,000 points per question. All right, if you send random data to a target. Okay, that's fuzzing. All right. Good. All right, what part of memory is LIFO? Okay, that's the stack. Good. All right, and where are the machine language instructions? All right, in the text section, that's correct. And what section of memory is read-only? Now that one I don't remember seeing on the slide, although it was probably there. This is an important fact. The text section is read-only. You are not allowed to write self-modifying code in any modern operating system. You're not allowed to modify the instructions while it runs. I used to do this all the time, but it's considered a terrible practice because you can't even print out the program and audit it. So the commands are not supposed to change while the program is running. So they make the text section read-only. In Windows, this is read or write. You cannot have read and write both on any memory segment, or you violate the security policy of the Windows operating system. You can allocate memory segments like that, but Windows doesn't like it and it doesn't do it by default. So the winners are PJ, and I know who that is. And if PJ is initials, it's probably good enough, and JC is probably initials. I think it is. So good. All right. All right. Well, let's see. It's about half past. I think we can do one more section before we take a break. And then I'll stop and see if anybody wants to add or anything. But we'll do one more section of this stuff first. All right. So let's talk about assembly code. So assembly language is the human-readable version of machine language. The binary machine language is the only thing the processor understands. And it's pretty hard for humans to read, so they turn it into assembly code, which is still pretty hard for humans to read, but this is as easy as it gets. There's 32-bit Intel, which is the most common code, although I think 64-bit code is becoming far more common, and they might be about tied by now. And then there are older systems like Spark and PowerPC and such, and then ARM, which is up and coming and used by telephones and a lot of Internet of Things devices, but most desktop computers are still running Intel architecture. Although the Mac now has their M1, and I don't think that's ARM. It might be. I'm not quite sure what the ARM. Yeah, that's right. What is the M1 running on? No, it's running on their new chip, and I think it's ARM. I'm pretty sure it is ARM. Anyway, all right. So Windows runs on x86 or x64. There is no ARM version of Windows, which is one of the big problems for people that want to run. Yeah, it's ARM. Yeah, people that want to run ARM on an M1, want to run Windows on an M1, have got a problem. although there is a virtualization platform that will do it, but I think it does it by emulating Intel on the ARM, and therefore you lose performance. All right, so an assembly language instruction looks like this: move ECX 0x42. The first thing is called the mnemonic. That is the command, what's happening, data is going to be moved. And then you have operands, ECX and 42. And this one is written in the format where the destination comes first and then the source. So this will take the immediate number 42 and put it in ECX. And that 42 is, by the way, hexadecimal. So it's 4 times 16 plus 2 instead of 4 times 10 plus 2. That's what the 0x means. So this will take the number 42 and put it in the ECX register, which is just a place you can store data. So this will, all right, move ECX is B9 in hexadecimal. There's a hexadecimal code for every command, and move ECX is B9. 42 is this. The bytes are in what's called Little Endian order, where the least significant bytes is here. This is 42. These are the number of 256s. This is the number of 256 squared, the number of 256 cubed. So this 32-bit number is written in this strange way. And so in binary, this instruction, move ECX 0x42, takes 5 bytes. B9 encodes move ECX, and all the rest of it is that immediate constant, 42. So this is what the processor actually sees, but this is what a human would rather see. Move ECX 42, it's easier to understand. So we talked about big endian and little endian a little bit. Big endian is where you write numbers the way you normally write them. If I write 64, I put 4 on the right because it's the number of ones. I put 6 over here because it's the number of tens. And if I move further to the left, I get bigger numbers. So in big endian order, this is the way you would write 42. 42 on the right, and if you have leading zeros, they all go on the left. Little endian is a very strange thing, not at all like any logical mathematical thing, where you just take the bytes here and you put the bytes out of order, but keep them intact. So this 42 moves to the left, these zeros move to the left, these zeros move to the right, those zeros move to the right. So now what you've got, if you were to write these 8 bits and those 8 bits and those 8 bits, their significance is not even monotonic. These 8 bits go from most significant to least significant, and then another group of 8 bits pick up from most significant to least. It's pretty messed up, but that's how it works with Little Endian, and that's what Intel processors use. And so you're going to spend all this course, you're going to be taking the order of bytes and turning them around to go backwards frequently. It's one of the annoyances you get used to. I doubt that it's really based on which side of an egg you eat first, but anyway. All right, so network data like 127.0.0.1 has big endian. The significant part of the address comes first, but numbers in these programs start with little endian. So it creates some strange situations. Like here's the loopback address, which has to be this in 7F001. So you send it over the network. You have to send the 7F first and the 1 at the end, or it won't be understood. But if you were to store it as a 32-bit integer in RAM, it would be stored like this, 01000007F. So flipping things from big endian to little endian is a common activity that you have to do to handle these numbers at the binary level. All right, so here's kinds of operands. You can have immediate values like 0x42 that is just this particular number. You can refer to a register. There are registers that can just store data, the AX, EBX, ECX, or you can have memory locations, as much RAM as you have, 4 gigabytes, 16 gigabytes, whatever you've got. Then you just put square brackets around the address. So I could have a literal address in here, or I could use a register as an address, and then I'd be referring to the memory location referred to by that address. So here's the addresses. EAX, EBX, ECX, and EDX came from the old days. There was just A. Now there's A, B, C, and D. These are general purpose registers. And then there's the base pointer and the stack pointer, which we're going to use a lot in this course. These refer to the bottom and top of the current stack frame for the module you're in, and we'll be using them a lot when we do stack buffer overflows. And the EIP. is very important. That is the address of the next command to be executed. The EIP is how the processor keeps track of what it's doing. So if I find some way to control the EIP, I can take over the machine because I can cause it to point to an instruction other than the one the developer intended for it to point to, and that gives me control of the box. So the general registers are just used for any purpose you want, A, B, C, and D. The segment registers keep track of sections. The instruction pointer we talked about. And these registers are all 32 bits because at the moment we're talking about 32-bit code for the older 32-bit architecture. And you can run 32-bit code on 64-bit hardware, natively in Windows and on Linux if you install the proper libraries. So a lot of people just write 32-bit malware because it'll run on 32 and 64-bit machines. All right, in 32-bit code, there are 4 general purpose registers. And by the way, if you want to, you can refer to these registers, parts of these registers, like the 8 bits at a time or 16 bits at a time, which is primarily used for compatibility with really old code written back on 8-bit or 16-bit machines. But as we'll see, there's a reason you'd want to use it when writing shellcode for attacks, because you can avoid having null bytes. Yeah. All right. Good. I see people. Good. Lots of good comments in the chat. All right. All right. So here's the whole 32-bit EAX register. And you can also refer to the lower 16 bits with AX and the 8-bit pieces of that with A low and A high. So you can perform 16-bit or 18-bit commands with a 32-bit processor, but normally you don't want to do that. All right, so typically you put in data or memory. You can put anything you want in there. There's a few special cases, like if you use multiplication and division, they use EAX and EDX in a special way. And when you call functions, functions typically return the result of the function in the EAX value. But that's just a convention. You can, in principle, use them any way you like. There's a status register called flags that keep track of things like whether the last operation resulted in 0, and things like that. You normally don't have to refer to the flags register directly. You just refer to it indirectly with things like jump not 0. So there's a 0 flag, a carry flag, a sign flag, and a trap flag are present in the flags register. And the instruction pointer, the most important one for us. This controls which command is coming up next, and therefore if whoever controls the instruction pointer controls the actual flow of the program. And that's what we're going to do, is we're going to find a variety of attacks that give you the ability to alter the EIP and therefore take over the box. All right, so let's do another one of these Kahoots, which is 1B. All right, let me just make sure it remembered to show you the answers. Okay, looked good. Ah, the music's back. Good. Uh-huh. Yeah, I see Rainbow Cache is making trouble. I'll have to restart this one. Yes, yes. Now you'll have to knock it off, Rainbow Cache. There is no defense, so I'm going to have to go down to the whining defense where you just ask them to knock it off. Which I remember this was fairly successful. There was a company that got hit by a DDoS attack, and they just put up a post saying on Twitter, "Oh, guys, come on, would you knock it off? We're like a nonprofit. We don't have any money." And it worked. They knocked it off. I think it was GitHub or something. Somebody DDoSed GitHub, and everybody said, "Oh, come on, why would you DDoS GitHub?" DDoS GitHub. So try again. Rainbow cache is a troublemaker. Yeah. A rainbow cache is one of those hackers you can negotiate with. Don't have to pay her $1 million a ransom to get her to stop hacking my Kahoot. All right. Looks like we're okay. Let's give this one a shot. All right, so what is the most common type of assembly language when you're writing malware? At least according to your textbook. This answer might be out of date by now, but I think it probably is still okay. Yeah, 32-bit, x86. All right. Yeah, not RISC, not yet. There will come a time when it's RISC, I suppose. All right, so there's the loopback. What kind of notation is that? Okay, that is big endian. The big number comes first, the small number at the end. This is the 127, and that's the 1. All right, so what are these things? Move, and an XOR. All right, those are the mnemonics, the verb part of the command. All right, what kind of operand is EAX? It's a register, okay? All right, what kind of operand is bracket EAX? All right, that's a memory location. All right, so, all right, JC is 1 twice. TV, they'll have to tell me who they are unless those are good initials. Do I know who that is? I think these are all initials. TV might be good initials too. All right.